Welcome to this comprehensive guide on scientific review papers. Today we're going to explore the different types of reviews, how to prepare them, and what makes them scientifically rigorous. First, let's understand what a scientific review paper actually is. A review paper is essentially a synthesis of existing research on a specific topic. Think of it like creating a map of a landscape that many explorers have visited. Review papers help researchers understand the current state of knowledge in a field without having to read hundreds of individual studies. They identify gaps in our knowledge, contradictions between studies, and suggest future research directions. There are 5 main types of review papers, each serving a different purpose. Let's explore each one in detail. The first type is the narrative review. This is the most traditional and flexible form of review. Narrative reviews synthesize broad literature without following rigid methodological protocols. Think of it like a skilled guide, telling you the story of a research field. These reviews rely heavily on the expert's interpretation and experience. The author uses their judgment to select and interpret studies. The narrative review flows from expert knowledge down to a narrative synthesis. It's flexible and can cover a broad scope of topics. Here's an analogy. A narrative review is like a documentary filmmaker choosing which scenes to include to tell a compelling story. The filmmaker has creative freedom, but must still represent reality accurately. The second type is the systematic review. This is much more structured and rigorous. Systematic reviews follow a clearly defined search and selection protocol that's specified before the review begins. The goal is to minimize bias through transparent, reproducible methods. Anyone should be able to repeat the review and get similar results. Here's the systematic review process visualized. You start by defining a precise question, search databases systematically, screen studies against inclusion criteria, extract data, and synthesize results. Systematic reviews typically use PRISMA or similar reporting standards. PRISMA stands for Preferred Reporting Items for Systematic Reviews and Meta-analyses. Think of a systematic review like a census that attempts to count every household according to strict rules, rather than sampling a few neighborhoods. Type 3 is the meta-analysis. This is a quantitative systematic review. Meta-analyses go beyond qualitative synthesis by statistically combining results from multiple studies into a single estimate. This provides more precise estimates of effect sizes and can resolve contradictions between studies. The basic concept involves calculating an effect size for each study. For example, Cohen's d is the difference between two means divided by the pooled standard deviation. Then we calculate a weighted mean of all effect sizes, where each study is weighted by its precision. Studies with larger sample sizes get more weight. Here we see 4 individual studies with their effect sizes being combined into a single, more precise estimate of the true effect. You might ask, why do we weight studies by their precision? The answer is that larger studies with more participants provide more reliable estimates. A study with 10,000 participants tells us more than a study with 50 participants. Type 4 is the scoping review. This is useful for emerging or interdisciplinary fields. Scoping reviews map the landscape of an emerging research area without necessarily evaluating quality. The goal is to identify key concepts, gaps in knowledge, and the types of research being conducted. Scoping reviews help us visualize the research landscape, showing where topics overlap and where gaps exist that need exploration. Think of a scoping review like early cartographers mapping uncharted territory. They sketch the general layout before detailed surveys are conducted. The fifth type includes critical and thematic reviews. These evaluate mechanisms, debates, and theoretical frameworks. Critical reviews don't just summarize findings, they evaluate the underlying mechanisms, theories, and assumptions in a field. They analyze ongoing debates, attempt to resolve contradictions, and critique methodological approaches. Often, critical reviews propose new frameworks or conceptual models that better explain the evidence. Critical reviews often synthesize competing theories into an integrated framework that resolves apparent contradictions. Now let's discuss how to actually prepare a review paper. This process applies to most types of reviews. Step 1 is to define a clear, focused research question. For systematic reviews, you can use the PICO framework: population, intervention, comparison, and outcome. For example, in adults over 50, do antioxidant supplements compared to placebo reduce cardiovascular disease risk over 5 years? You might wonder, why must the question be so specific? Because vague questions lead to scope creep and unfocused searches. A specific question guides every subsequent decision. Step 2 is collecting and filtering relevant, peer-reviewed sources. Search multiple databases like PubMed, Web of Science, and Scopus to ensure comprehensive coverage. Use Boolean operators to combine search terms. For example, antioxidant and cardiovascular and randomized. The filtering process is like a funnel. You might start with thousands of articles and progressively narrow down to the most relevant studies. Apply inclusion and exclusion criteria consistently to all studies. Document reasons for exclusion. Step 3 is organizing your sources into conceptual themes. Group studies by shared topics, methodological approaches, or outcome measures. Create a coding framework or data extraction table to systematically record information from each study. Organize your review around major themes. Each theme becomes a section in your paper. Step 4 is comparing findings across studies to identify patterns and discrepancies. First, look for consensus. What do most studies agree on? These are the established findings. Then, identify contradictions. Where do studies disagree? Try to explain why. Always consider study quality and potential biases when weighing evidence. Not all studies are equally reliable. When you find contradictions, investigate why. Different populations, methods, or outcome measures can explain discrepancies. Step 5 is explicitly highlighting gaps in knowledge and unresolved contradictions. Ask, what populations or contexts are understudied? Where are there no data? What methodological limitations persist across studies? Are there common weaknesses? Where do theoretical explanations fall short? What phenomena remain unexplained? A good review clearly delineates what we know from what we don't know, helping future researchers focus their efforts. Step 6 is synthesizing everything into a coherent, logical storyline. Structure your narrative to start broad and progressively narrow to specific questions and findings. Build arguments logically from the evidence. Each claim should be supported by citations. End with clear implications for practice or policy and specific suggestions for future research. The typical structure flows from introduction through background, findings and conclusions, and a logical progression. Let's explore some key equations and quantitative concepts used in reviews, particularly meta-analyses. The I-squared statistic measures heterogeneity between studies. It tells you what percentage of variation is due to real differences versus chance. Interpretation: 0 to 25% is low heterogeneity, 25 to 75 is moderate, and above 75 is high heterogeneity. High heterogeneity suggests the studies are too different to meaningfully combine into a single estimate. Egger's test for publication bias examines whether small studies with negative results are missing from the literature. Publication bias is the tendency for journals to preferentially publish positive findings, which can skew meta-analyses. A funnel plot visualizes publication bias. In an unbiased literature, small studies should scatter symmetrically around the true effect. Let's work through a numerical example of calculating and combining effect sizes. Imagine study 1 finds a treatment group mean of 85 and control group mean of 78. The pooled standard deviation is 12. Cohen's d equals 85 minus 78 divided by 12, which equals 0.58. This is a medium effect size. Study 2 has a smaller sample and calculates d equals 0.42. We weight each study by the inverse of its variance. Larger sample sizes have smaller variance and get more weight. Let's say study 1 has weight 100 and study 2 has weight 50 based on their sample sizes. The weighted mean is 100 times 0.58 plus 50 times 0.42, all divided by 150. That gives us 0.53. The combined effect size is 0.53, with a much narrower confidence interval than either individual study. Let's discuss the implications of review papers for science and society. Review papers, especially systematic reviews and meta-analyses, inform clinical practice guidelines and policy decisions. For example, Cochrane reviews are considered gold standard evidence and guide medical practice worldwide. By identifying what's already known, reviews prevent researchers from duplicating existing work. They accelerate the pace at which scattered findings are synthesized into actionable knowledge. The pathway from primary research through reviews to clinical guidelines and ultimately patient care shows the real-world impact of review papers. Let me highlight some common pitfalls when preparing review papers. The first pitfall is cherry-picking studies that support your preconceived hypothesis while ignoring contradictory evidence. Second is failing to assess and report the quality of included studies. Not all evidence is equal. Third is mixing different outcome measures as if they're equivalent. Quality of life is not the same as mortality. Fourth is ignoring heterogeneity and combining studies that are too different. Fifth is not updating your literature search before publication. New studies may have appeared. Now let's discuss best practices to ensure your review is rigorous and valuable. Register your protocol in advance on platforms like Prospero for systematic reviews. This prevents outcome switching. Use at least 2 independent reviewers for study screening and data extraction to minimize bias. Calculate and report inter-rater reliability using kappa statistics to show agreement between reviewers. Cohen's kappa measures agreement beyond chance. Values above 0.8 indicate excellent agreement. Conduct sensitivity analyses by removing low-quality studies or outliers to see if conclusions change. Use grade framework to assess the overall quality of evidence as high, moderate, low, or very low. Finally, let's look at emerging trends and future directions in review methodology. Living systematic reviews are continuously updated as new evidence emerges, providing always current syntheses. Machine learning algorithms are being developed to assist with title and abstract screening, dramatically speeding up the process. Network meta-analysis allows comparison of multiple interventions simultaneously, even when not all have been compared head-to-head. Individual patient data meta-analysis, where raw data from studies is pooled, provides more powerful analyses than aggregated data. Network meta-analysis can indirectly compare drugs A, B, and C even if they were never compared directly in trials. Let me summarize the key takeaways from this comprehensive guide. First, understand that different review types serve different purposes. Choose the right type for your question. Second, systematic approaches with transparent methods minimize bias and increase credibility. Third, quantitative synthesis through meta-analysis provides more precise estimates than individual studies. Fourth, the best reviews acknowledge limitations and suggest specific future research directions. Finally, rigorous reviews translate directly into improved policies, practices, and patient outcomes.